Abdullah, for SAT exams, requirement is just class 12. You should be 12 passed only. Like during your 12, you can also do SAT exams. Like in a year, you can give SAT exams for twice, I guess, 2 or 3 times in a year. Subjects for SAT, English, maths, and some basic sciences like physics and all. Only English is. Otherwise, maths and physics, chemistry are very, very easy. Okay, and please revise whatever we did in the last class. Like we did circuits having inductor only. Just revise it. We'll do numericals on this. Hamna and Mirdula. Bacho, your class is not on this meeting ID. Huh? Nishkash is sharing your meeting ID with you.
Okay, sir.
Okay. Yes, Abdullah, it's easy to score that much in SAT. Just remind me to send you a sample paper of SAT. I will share a sample paper of SAT with you. So it's very easy. Only English. English is the questions of English have some standard. Otherwise, maths and physics and chemistry are very, very easy in the SAT 1 exams. So we did a circuit having resist inductor only. In this circuit of inductor, this is EMF E0 sin omega t. Nazira, do you remember what was the phase difference between EMF and current in this circuit? Nazira, do you remember Nazira,
Yes,
phase
sir.
difference between current and EMF? Yes. What was the phase difference?
0.
0. Inductor.
No.
Yes. How much was the phase difference? Phase difference was, this is the phase difference, right? Yes, Nazira. How much is the phase difference between EMF and current? No, Nazira won't tell. Mariam.
Yes, sir.
The phase difference between EMF and current?
Pi by 2.
Pi by 2. Which one lags?
Current.
Current lags by a phase difference of pi by 2. So for the circuits, you should remember these relations. First one, you should remember first of all this relation. Then you should remember this relation. The phase difference between EMF and current is pi by 2. Current lags by EMF. Then you should remember this relation, that reactance is omega L. What is reactance? It's like resistance, analog of resistance. Like obstruction offered by inductor is reactance. How you calculate inductance, reactance, it's omega into L. Amalia, what is omega here?
Angular velocity.
Not angular velocity. You can say it angular velocity, but here we write something else. What we call it, Abdullah? Omega?
Yes, an angular frequency.
Angular frequency. Well, in this particular case, angular velocity and angular frequency are same, but throughout AC, authors will always write omega as angular frequency, not as angular velocity. Although your answer was not wrong, Amalia, but remember angular velocity and angular. Here we will use angular frequency. Third, you should remember this relation. Next, you should remember this relation, that peak value of current is E naught divided by XL. What is E naught, Ahmed? What is E naught here?
EMF.
Peak value of EMF, Ahmed. Huh? Shehzada, did you revise this circuit? No. Shehzada, I can't hear you. You're not audible.
I didn't realize.
You didn't revise. Shehzada, start your self-study, which you have exams after almost a month. Like you would be having your first term exam mid-November. So you just have October to prepare. Already, if chapter number 1, 2, 3, these are very lengthy chapters that you have to revise. At least do these chapters in a way that they are very solid, like 6, 7 chapters, chapter number 6 and chapter number 7. Okay, next is phase difference. You know, power factor is 0 here. Average power is also 0. Next, first of all, we have few conceptual questions on this topic. Like first off, I'm discussing all those topics as notes. You may be asked to plot XL versus omega graph. The relation between XL and omega is this. XL is equal to omega L. Noor, can you plot this graph? What should be the shape of this graph? This is omega and this is XL. Yes, Noor. Can you predict the shape of this graph? Noor is not there. Okay, sorry. Ahmed, can you predict the shape of the graph?
So 1 minute.
XL is omega L. I'm plotting XL versus omega graph. Can you predict the shape of the graph?
So it would be a straight line
Why it would be a straight line?
because XL is directly proportional to omega.
Both have single powers, right? Linear equation. So graph would be a straight line. Next, maybe you may be asked to calculate the slope of this graph. Abdullah, can you calculate slope of this graph?
Yes, sir.
Yes, what would be the
Sir,
slope?
XL by omega.
XL by omega. See, slope is tan theta, which is always the quantity on the y-axis by quantity on the x-axis. So it's XL by omega. And from this equation, what is XL by omega from this equation, Fatma? From this equation, what is XL by omega? Fatima. 1. See, XL by omega, it's 1 or L?
L.
L, self-inductance. So this is it. Slope of the graph is XL by omega, which is equal to L, self-inductance. Similarly, you can be asked to plot XL versus frequency graph. See, you can write XL as 2 pi nu L. So what's the relation between XL and frequency? They are directly proportional. Now, if they are directly proportional, so the nature of graph would be a straight line. So again, if you calculate slope of this graph now, slope will be equal to tan theta, would be equal to XL by 2 pi, not XL by 2 pi, XL Here L is in subscript. This L is in subscript. Y-axis divided by x-axis. On x-axis, you have frequency. So this is XL by frequency. What is XL by frequency from this equation, Nazira? Nazira, how much is XL by frequency in this equation? Oh, very good. Not 2 nu, not 2 pi L. Na? When you take nu in the denominator, then this is 2 pi and L. So that is the slope of the graph. After this, you can get one more conceptual question, that is behavior of inductor at high frequency. So XL is C 2 pi nu L. If frequency is large, that means XL is large. So if you pass a current of very high frequency through an inductor, then that inductor will offer very strong opposition. Reactance would be large. If XL is large, then if I write current, current is mu naught E naught divided by XL. Shahzada, if the value of XL is very large, can you predict the value of I naught? I naught would be very large or I naught would be small, Shahzada?
Sure, it will be small.
It would be small. So if XL is large, very large, I naught is extremely small. Extremely small. It acts like an open circuit. It acts like an open circuit. This will work like an open circuit. So at a very high frequency, this will behave like an open circuit. At a very high frequency. Open circuit means your switch is off, because if current is very small, then you can consider it like you have switched off your system. Your circuit is off. If I take for small frequency, if frequency is small, then what about XL? XL is 2 by nu. XL is small. And we know that current is E naught by XL. If XL is extremely small, if XL is extremely small value, then what about I naught, Sania? If XL is extremely small, then what about the value of I naught? I naught would be extremely small or it would be extremely large?
Extremely large
Why, Sania? Why it would be extremely large?
because X is small.
They are inversely proportional, right?
Yes.
I naught is extremely large. Extremely large. This is it. Just note it down. So these are few conceptual questions that one can get on this thing. Sania, you have connected a bit late, so I have started from this thing only. Yeah, this is the first stop.
Okay, sir. Thank you.
Note it down.
Sir, can you scroll up?
Noted.
Yes, sir. Done.
Okay, so if your current is extremely large, then it will act like there is no resistance. Extremely large, no resistance. Or you can say it will behave like short circuit. It will behave like short circuit. So these are few conceptual questions, then one can get on this inductor. Now let's solve this numerical. So you have an inductor of 10 Henry is connected to an AC supply Noor, you just missed some conceptual questions, huh? You missed basically 4 conceptual questions on inductor. Inductor that we were doing the last class.
Okay, sir.
So AC supply is 20 sine 314t. This is the AC supply, volt. You're supposed to calculate what is the peak value of EMF here, Shahzada? In this equation, can you decide which one is the peak value of EMF?
So 20.
20, good. And what is the frequency? Angular frequency? 314, okay?
3 on 4.
Calculate first part. Inductive reactance. Inductive reactance. Second part. Peak value of current. Peak value of current. Third part. RMS value of current. Then equation of current. And the last part, average power dissipated. Average power dissipated. Then we need average power dissipated. So inductance is 10 Henry. Omega is 314. Radian per second. First part. How much is XL now? Fatma will tell. Fatma, what's the relation for inductive reactance, XL? Fatma, just turn your notes and see what is the formula for
Omega L.
Omega L. Very good. See, this is inductive reactance. Right? It's omega L. So this is omega L. XL is omega into L. Your omega is 314. This is 10. And you get 3140 ohm. That's XL. Second part. Sania, how would you calculate peak value of current? Peak value of EMF is known. How do you calculate peak value of current, Sania?
ERMS.
See. This is the peak value. For a circuit having inductor only, when you have EMF, see, peak value of current is peak value of EMF divided by inductive reactance, XL. So this is your I naught, which is E naught divided by XL. How much is E naught, Sania?
20.
20. And how much is XL?
XL is 3140.
So when you cancel them, it's 1 by 57 amp. That's a peak value. 2 by 314 is 157, I guess. Yes. Okay, Mariam, if you have peak value of current, you know peak value of current is 1 by 157 ampere. Can you calculate RMS value from peak value? Mariam?
Yes, sir.
Yes. What is the RMS value if you have peak value? Mariam, it's a straightforward thing. You have I naught, you need RMS. This was in the very first class of AC. This one. Where is RMS value? This is the RMS value, na? This is how we calculate RMS. So Mariam,
Yes,
tell
sir.
me, what's the formula for RMS? This is RMS value of EMF, right? How would you calculate RMS value of current?
Multiply by 0.707.
Either you can divide it by √2. So it's 0.707 of I naught. So it seems like Mariam, Shahzada, you two are not doing any self-study, right? So maybe in a day or two, I will allot some self-study companion for you people. So they will sit and monitor during your self-study time. Otherwise, you will spoil this exam. Maybe Nishkarsh will call you for a self-study companion. Ahmed, I don't think you need it right now, but okay, if you want, I can allot someone for you too, but and it's a punishment. So that self-study session will last for 4 to 5 hours. Mariam and Shahzada for you both.
Okay, sir.
And if you miss that session, I will talk to your parents.
So when is it?
Maybe on tomorrow or day after tomorrow. Now, Friday will not be a holiday for you. Unless you are performing well in class, Friday is not a holiday. Work like we Indian do. Huh? We don't have Sunday, Saturday, nothing. We work on weekends also. Okay, so that's RMS. Equation of current. What is the equation of current? We'll tell. Sania, you too. Okay. What is the equation of current? Equation of current. We'll tell. Noor,
E0.
equation of current. I is I
Minus
naught.
I0 cos omega.
Sine.
I naught omega sine omega t minus pi by 2. Where is this equation? This equation is here. Here, minus pi by 2. So you have I naught. I naught we know this is 1 by 157.
So why are we not using I naught sine omega t?
Because in this circuit, current is not I naught sine omega t. You see, we have derived this thing. In a
Okay, inductor only.
Yeah, for inductor only.
Okay.
For resistor, it was I naught sine omega t. But in inductor, your EMF and current are not in same phase. So if you take your EMF as E naught sine omega t, then you can't write your current as I naught sine omega t. You can write this as sine omega t minus pi by 2, or yes, you can write it as minus of cos omega t. Yes, we convert this minus of cos omega t into this thing. It's your choice. You can write it as sine omega t minus pi by 2, or you can write this as minus of cos omega t. That's the same thing. Omega t minus pi by 2. Or as Noor says, you can write this as minus 1 by 157 cos of 3 fun 4 t also. This is your current. And what about the fifth part? This is the easiest. Shahzada will tell. Shahzada, average power for this circuit. Yes, Noor. Average power is 0. Do it. So that's a straightforward numerical on this inductor.
So how is average power equal to 0?
Because we have derived this result. The power factor is 0. Phase difference is pi by 2. Power factor is 0. That's why average power is 0. So whenever you just have an inductor in the circuit, there is no average power. Power dissipation is 0.
Yes, sir.
Okay, first write this question and then the solution. We'll do one more numerical on the same concept. Then we'll do circuit having capacitor. See, that self-study company is a subject expert. So if I'm allotting you someone for physics, he knows physics, right? He's not a faculty, but he knows physics. So you can ask your doubts also with him. He can help you even in numericals, or if you have any doubt, you can ask your companion.
Yes, sir.
Noted?
Yes, sir.
Okay. Alhamdulillah, Nishkar is sharing that sample paper of SAT with you. Within half an hour, is sharing.
Thank you, sir.
And you all should appear for SAT exams if you're planning your graduation from Europe or somewhere.
Sir, you can share with me as well.
Okay.
So can you scroll up?
Yes. No, Noor, SAT is easy. If your maths and physics is good, then SAT is easy. The only standard question in SAT is from English, nothing else. Nishkash must be sharing that paper in within 1 hour or half an hour in the group. Just look at that SAT paper. It's easy. It's not tough. Okay. Is it clear?
Yes, sir.
See the next thing. So that was let's do one more question on inductor. So the next question is an inductor. I'm just coming to it, Amit. I'm just coming to it. An inductor of 5 Henry is connected AC supply no, not this AC supply, to AC supply of 50 volt and 50 hertz. What is this 50 volt? Is it the peak value, RMS value, average value? Which value is this 50 volt?
Peak value.
No. If a value is given in AC and it's not mentioned which value is this, that means it's the RMS value. It's not a peak value.
Okay.
And what is the unit of inductive reactance? Yes. What is the unit of inductive reactance? Ohm. It's a resistance. So unit
Ohm.
is ohm. Remember these small things. Inductive reactance. After inductive reactance, you need to calculate RMS value of current. Then do peak value of current. After peak value, do inductive reactance is done, RMS value is done, peak value is done. Next is equation of current. Write equation of EMF and current. Now let's see. Solve it and write your answer in chat. It's a lengthy question. It can take some time. Do it.
So what is that 50 volt and
50 hertz. So this 50 volt is the ERMS value. Okay. And this 50 hertz is the frequency. If you have frequency, you can calculate angular frequency using this to kind of Okay, Fatima, Amalia, first is correct. Yes, Noor is also correct. Okay, Sania, it's correct. Ahmad, first part is correct. Second, I don't think that second is correct. Yes, Noor is correct. Second part is correct. Ahmad, just check your part. Mariam, first part is correct. Noor, third. Okay, let me check third part. Yeah, Shehzada, this part is correct. First is correct. Nazira, first is correct. Try all parts, huh? Good note. Fourth is also correct. How much second? Let me check. Abdullah, are you solving it? Abdullah,
Yes, sir.
you solving it?
Yes, sir. I got the answers, but the value is a little
Okay.
like it's difficult for me to type this.
Okay, let's solve it. See, for the first part, it's given that L is 5 Henry, self-inductance is 5 Henry, and your frequency is 50 Hertz. So if frequency is given, that means angular frequency is given. Frequency is 50 Hertz. If frequency is given, that means angular frequency is given, which is 2 pi nu. So that will be 2 into pi, which is 3.14, into nu, which is 50. So that is 314 radian per second. That's the first part. So for the first part, you need to calculate inductive reactance. Inductive reactance XL is omega L. So your omega is 314. Your 314 only, yeah. It's 314 into 5. So 314 into 5 is 1570. So that's XL. Second part, you need IRMS. Also, ERMS is given. ERMS is 50 volt. ERMS is also given, which is 50 volt. So you can calculate IRMS also. IRMS is ERMS divided by XL. ERMS is 50. XL is 1570 ampere. That's IRMS. After IRMS, you can calculate peak value also. IRMS is I naught over root. So you can write that I naught is root 2 into IRMS. It's root 2 multiplied by IRMS, which is 50 by 1570, this much of amp. After peak value, I need equation of EMF and current. See, equation of EMF is this: E is E naught sine omega t. If this is the equation of EMF, you can write, you need E naught. So for E naught, you can use this ERMS. You can say that E naught by root 2 is ERMS. So you have E naught by root 2 is ERMS. How much is ERMS? ERMS is 50. So you can write that your E naught is, it's 50 root 2 volt. Now substitute values here. Instead of E naught, substitute 50 root 2 sine omega. We already know it's 314. 314. This is the fifth one. So it's 50 root 2 sine 314. No, not the fifth one, but the equation of current. For equation of current, you need I naught sine omega t minus pi by 2. That is the equation of current. So you can substitute all values here. How much is I naught? It's root 2. This gets cancelled. 5 by 157 into root 2. So it's 5 root 2 by 157. It's sine omega 314 t minus pi by 2. Note it down and tell me if you have issue in any part. Because if you have issue in this numerical, then the next topic would be tough for you. Next, we have capacitors. If you can understand inductor, then capacitor is very easy.
Sir.
Similar type of things. Yes.
Sir, the last question, fourth part, can you show?
Yeah.
No, sir, the previous question.
Previous question.
Oh, okay, sir. Okay, sir.
Okay, note it down now. And tell me if you have issue in any part.
So where is the second equation? Like IRMS is equal to VRMS by XL. Where did we say that?
Yeah, that is the equation of current. Like, I haven't mentioned this equation, but if you can write peak value of current as E naught by XL, then you can write RMS value also is peak RMS.
Okay, sir.
Noted?
Yes, sir.
Yes, sir.
Okay, write this one also. So that was a circuit having inductor only. Similarly, the next circuit will be circuit having capacitor. Capacitor is just like inductor. Same phase difference of pi by 2. Only instead of lag, current will start to lead. So AC circuit having capacitor only. Capacitor. So you have a capacitor and you connect this capacitor to an AC supply. AC supply is this is E naught sine omega. So here your motive is to get the equation of current. For equation of current, first of all, let's calculate charge stored in the capacitor. Charge stored Q is CE, or you can write this as CE naught sine omega t. So this is the charge stored in capacitor. The charge stored here is CE naught sine of omega t naught. So once you have charge, you can also calculate current. Current would be dq over dt. It's d over dt of CE naught sine omega t. You can take this C outside, E naught outside. You are left with only it's d over dt of sine omega. So you can write this as this is C naught. Derivative of sine omega t is omega into cos omega. So you can write this as it's omega c into E naught into cos omega. See this omega into c, you can write this as it's E naught divided by 1 by omega c. I can write this thing as, because this omega c will go to numerator and you will get the same equation. It's cos of omega. So this E naught, this 1 by omega c, now we'll get capacitive reactance. Just one thing. I can write this cos omega t in terms of sine as, I can write this as sine of omega t plus pi by 2 now. And substitute this value here. So I will get I is E naught by 1 by omega c. See, our motive is to convert this cos in terms of sine always. I'm converting this in terms of sine because I can compare it with this, the equation of EMF, which is in terms of sine. whether the current is in same phase with EMF or not, whether current is leading EMF or it's lags by EMF. That you can do only if you convert it in terms of sign. So it's sine omega t plus pi by 2. This is the equation of EMF. Now see here. In inductor, we had inductive reactance. In capacitor, we have capacitive reactance. Here we have capacitive reactance. I can write capacitive reactance as Xc, and this is 1 by omega C. This is capacitive reactance. Its SI unit is ohm. So for resistor, we use resistance. For inductor, we use inductive reactance. For capacitor, we use capacitive reactance. SI unit is ohm. So that's Xc, which is 1 by omega C. We can calculate the peak value of current. Peak value of current here is E naught by Xc. In capacitor, it was E naught by XL. Now we have E naught by Xc for capacitive reactance. If I do this substitution, I call this as equation number 1. Let me call this as equation number, not this one, 2. Let's call this as equation number 3. If I substitute this here, I can write this as, if I substitute 3 in 2, then I can write the equation of current as I naught sine omega t plus pi by 2 now. That's the equation. So if you look at this equation carefully, this is equation number 4. When you compare 1 and 4, can you decide on comparing 1 or 4 whether current and EMF are in same phase or they lead or lag something?
They're out of phase.
They're out of phase. What's the phase difference between them?
5 by 2.
5 by 2. In EMF, it's E naught sine omega t. In current, instead of omega t, you have omega t plus pi by 2. So they are out of phase by pi by 2. Note it down. Then we will do that next thing. Phase difference, phasor diagram, equations and everything. Just note it down. So for numericals, you need to remember this relation of this one, like this relation. You should remember this relation and you should remember this equation. That's it. The rest is the part of derivation. Note it down and tell me once you have it.
Sir, can you scroll down?
Amalia, just by looking at the face, like here, for the equation of EMF, the phase is omega t. Huh? When you get the equation of current, it is omega t plus pi by 2. So they are out of phase by pi by 2. Okay, Malia?
Yes, sir.
Yes, Noor. See, Noor, this is omega into C. Now I can write this as 1 by omega C first. If I see I is E naught, right? By 1 by omega C. I can take it to the numerator and it will be same omega C naught. Basically here I want to write it in terms of the standard form of E by R type. Like current is EMF by resistance always. That's why I want to take it to the denominator to show that this is the term resistance like term, inductive reactance like term.
Okay, sir.
Yeah. Ahmed, IELTS is just for the English language test. When you are going to European country or America, then they just want to know whether you know English or not. That's IELTS. The score, valid score of IELTS is for that. But when you are taking admission in graduation courses, right? You along with IELTS, you need a score of valid score of SAT also. IELTS is just for English, nothing else. Even I have to give IELTS. Even if I want to apply for my postdoc in somewhere, they will ask me to for my IELTS score. Yes, SAT is very important. SAT is very important. You should have a good SAT score. Most of the universities will need SAT score. Okay, now let's calculate phase difference, phasor diagram, and everything. Now let's calculate phase difference.
Sir, can you scroll up?
More?
No, sir, enough. I'm done.
Okay, next. Phase difference. So here EMF and current are not in same phase. Current actually leads EMF by a phase difference of pi by 2. So here current leads EMF by pi by 2. So if I draw phasor diagram, then this is the phasor diagram. This is EMF, E naught. This angle is omega t. Current is leading EMF, so that's I naught by phase difference of pi by 2. So this is the phasor diagram. After phasor diagram, he can ask you to draw sine curve. See, for EMF, the equation is E naught sine omega t. For current, it's I naught sine omega t plus pi by 2. So sine omega t plus pi by 2 means cos omega t. So the sine curve is for EMF, this is standard curve, right? This is sine curve. This is for EMF always. This is the peak value of EMF. This is 0. This time is t by 4. T by 4. This is t by 2. This is 3t by 4. And this is t. This is for EMF. For current, we have to draw the cos curve. So this is the cos curve. This is the cos curve. So see, when your EMF is 0, your current is maximum. When your EMF is 0, your current is maximum. Out of phase means when you phase difference of pi by 2 means when your current is 0, your EMF maximum. When your EMF is maximum, see your current is 0. After this simultaneous sine curve, phasor diagram, next term is we have sine curve, we draw phasor diagram. The next thing is
Power factor.
power vector. Thank you. The next is power vector. Is power vector. So see, phase difference is pi by 2 now. Phase difference is pi by 2. Phi is pi by 2. And power factor is just cos phi, na? Cos phi. Cos pi by 2. Just like inductor, power factor is 0. Average power. ERMS, IRMS, cos pi by 2. Cos pi by 2 comes out to be 0. So that's average power. So just like inductor, here also power dissipation is 0. We call this type of current as Wattless current. For inductor also, where P average is 0, write that this is Wattless current. Just turn your page. And for circuit having inductor, here. Yeah, here. Write that this is Wattless current. So current for which power dissipation is 0 is Wattless current. So till now we got two Wattless current. One is circuit having inductor only, another is circuit having capacitor. So having written that, there is just one or two more things. Then we can discuss the behavior of capacitor for high frequency. No. We can plot the graph also. Na? See, Xc is 1 by omega C. What should be the shape of the graph, Noor? Inversely proportional. What would be the shape of the graph?
Hyperbola.
Hyperbolic, right? This would be the shape of the graph. Slope will give nothing. But if I ask you to plot Xc versus 1 by omega, for 1 by omega, this is directly proportional. Graph would be a straight line. Remember this thing. With omega, graph is hyperbolic, but for 1 by omega, it would be a straight line graph. Okay, once you have this thing, then the last is the behavior for high frequency and low frequency. High frequency. High frequency means your omega is large. It's very, very large. If omega is large, then Xc is 1 by omega C. If omega is large, that means your Xc is small. Xc is small. If Xc is small and if I calculate current is E naught by Xc, that means I naught is large. Large current means it will behave like a short circuit. If you remember inductor, for the same high frequency, inductor was acting like an open circuit, but it will behave like a short circuit. After high frequency, you can write for low frequency. For low frequency, it will be opposite, like Xc will be large. Your I naught will be very, very small. It will behave like an open circuit. So you should remember these results, like how capacitor behaves for low frequency, how capacitor behave for high frequency. For high frequency, it behaves like an short circuit only. For high frequency, it behave like there is no obstruction in the flow of currents, behave like a short circuit. When I say short circuit, that means a conducting wire. But for low frequency, it's behave like an open circuit. It's a very, very large resistance. There is one more thing. For DC. DC means which does not change. So omega is 0. For DC, your XC is 1 by omega C, 1 by 0, so it's infinite. So capacitor offers infinite reactance to DC. Capacitor offer infinite obstruction to DC. It simply block DC current. DC cannot pass through a capacitor. Capacitor simply block DC current, but it allow AC to pass through. These are some important conceptual questions from this topic. Okay, do it now. Note it down. Tell me once you have written.
Sir, can you scroll down?
Yes. Okay.
Yes, sir. Yes, sir.
Hmm. So these all are conceptual questions on capacitor. There's one more thing. Since it allow large current to pass through it for high frequency, it's known as sometimes known as high band pass filter. Very rare chances can someone ask about it. The high band pass filter. High band pass filter simply means it allow high frequency to pass through it. And inductor was low band pass filter. You can note that thing in the notes of inductor. Inductor was low band pass filter.
Sir,
It
how
allowed low
capacitor?
frequency to pass through it. For small frequency, it was acting as a short circuit. So you can say that it was low band pass filter. We use these terms when we study communication, but you should remember these things.
The inductor is a low band pass filter.
Low band pass filter because it allows low frequencies to pass through it. See, for small frequencies, current is extremely large. Inductor is low band pass filter and capacitor is high band pass filter. Okay, now let's do some basic, very basic numericals on it. So you have a capacitor.
Sir, what was that? Low band pass filter.
Pass filter, yes. Low band pass filter. Low band pass filter means it allow low frequency to pass through it. Inductor was low band pass filter. Low frequency, a capacitor is
So I
yes.
didn't write the low frequency part.
Okay.
So Xc is equal to 1 by omega c.
0 into c. Because omega is 0, xc is 1 by omega c. So I wrote 1 by, instead of omega, I write 0. 0 into c. So 1 by 0 is infinite, so xc is infinite. For DC, inductive capacitive reactance is infinite.
Okay, so
Sure. This is over. Do this numerical. Straightforward thing. A capacitor of 10 microfarad is connected. For capacitor, convert microfarad into farad. It's connected to AC supply.
So that is 10.
Yes, Abdullah.
That is 10 farad.
10 microfarad. To remove micro, multiply with 10 raised to the power minus 6. This is the AC supply. It's 20 sine 340 in T. Calculate first part. Capacitive reactance. Similar question, just instead of inductor, you have capacitor. Capacitive reactance, second part. Peak value of current. Peak value of current. Third part. Micro means minus 6, power is minus 6. Milli is minus 3. Huh? RMS value of current. Fourth. Equation of current. Fifth. average power dissipated. Okay, do it now. Okay, Noor. Correct. First is correct. See, if dividing by 314 is taking too much of time, you can just write in terms of 314 only. Okay, I have no problem. Ahmad, convert this micro into farad, multiply with 10 raised to minus 6. Wrong. You're wrong. Abdullah, omega is 314, yaar.
Sir, I did to 100 pi.
100 pi.
Yes, sir, I took 100 pi.
Okay. Fatma, it's 10 microfarad multiplied with 10 raised to minus 6, na? Fatma, it's 10 raised to minus 6. So it will be 10 raised to minus 5 in the numerator. Check your calculations. Fatma, it's 10 into 10 raised to the power minus 6. Okay, Ahmed. At least try every part once, then I will solve. Shahzada, are you solving it?
Yes, sir.
Right, at least first part, na? Right, at least first part of it. Okay, let's solve it together. Huh? So you have a capacitor of 10 microfarad. So this is 10 into 10 raised to the power minus 6. 10 raised to the power minus 5 farad. How much is omega? Omega is 314 radian per second. E naught is 20 volt. Huh? $20 volt. First part of the question. How much is XC? XC is capacitive reactance is 1 by omega C only. So omega is 314. Your C is 10 raised power minus 5. When you take it to the numerator, it will be 10 raised power 5 by 314 ohm. First part. In the second part, you need I naught, right? I naught is E naught divided by XC. E naught, how much is E naught? E naught is 20 divided by XC, which is 10 raised to the power 5 into 314 ampere. Third part, you need IRMS. Or if you want, you can write this as 314 into 2 is 628 into 10 raised to the power minus 4 ampere. IRMS is I naught over root 2. Or you can write this as 0.707 into I naught. That's your choice. So that is 628 into 10 raised to the power minus 4 over root 2 ampere. Fourth part, equation of current. See, equation leads EMF. So the equation is I naught sine omega t plus pi by t. So how much is I naught? That's 628 into 10 raised to the power minus 4 sine of omega, which is 314 t plus pi by 2. Or you can write this as cos also. Huh? Average power dissipation in this circuit is also. See, these are very basic circuit: resistor, capacitor, and inductor. The next circuits that you have will be the combination of all. You'll be having series LCR circuits, like circuit having combination of inductor, capacitor, and resistor. Just note it down. Then we'll do one more, or we will do now the combination. Then we'll do start the LCR circuit now. Just note it down. Abdullah, in LCR, we have both series as well as parallel. Parallel is not a part of this syllabus. You have series LCR. You did parallel in your school. No, Abdullah, it's not tough. Like, it's not tough. The similar type of calculations. For doing series and parallel, you should remember that this voltage and EMF will behave like vectors. The next is series LCR circuit. See what is series LCR circuit. In series LCR circuit, you have all three elements: inductor, you have capacitor, you have resistor, and they are connected in series. So you have an inductor, you have capacitor, and you have resistor. They are connected in series. For doing series LCR circuit, you should know vectors. Here, voltage and EMF and current will behave like vector quantities. You should remember parallelogram law. Like if you have two vectors, vector A and vector B, acting in opposite directions. So when you add them up, their magnitudes get subtracted. This is vector addition, right? If you have two vectors which are at 90 degree, you did this in class 11 that your resultant is root over A square plus B square. So this is the resultant vector. So this is inductor, this is the capacitor, and this is the resistor. The equation of EMF is E naught sine omega. So instead of EMF, now we start with the equation of current. It's a bit lengthy calculation. We start with the equation of current, I naught sine omega t naught. See, they are connected in series. So the same current will flow through each one of them. Same current will flow through each of them. I, same current I here, same current I here. Now, there will be voltage drop across each circuit. So voltage voltage drop across inductor. So voltage drop across inductor, you can write as V naught L. V naught is I naught XL. That's my first equation. Next, you need voltage drop across resistor. For resistor, we write IR. So we can write that voltage drop across resistor is I naught R. V naught means peak values. Peak voltage drop, peak voltage drop. Similarly, we can do it for capacitor. Across capacitor. For capacitor, we can write this as I naught XC. See, if you use Ohm's law, then voltage is I into R. For resistor, it's IR. For inductor, it would be instead of R, you are using XL, so it should be I naught XL. For capacitor, you need XC, so it will be I naught XC. So these are the voltage drop across individual circuit. Note it down, then we will see how we add these all voltages. Note it down. For adding these voltages, we would be using a parallelogram. Okay. The next task is to add these vectors. So first of all, write this statement. Due to phase difference, EMF, voltages behave like vectors. So you can't add them up algebraically. To add them up, you need vector laws. So do you remember what's the phase difference between current and voltage in inductor? Are they in same phase? In resistor, they are in same phase. Current and voltage are in same phase. What's the phase difference between them?
90 degree.
So in inductor, current is leading EMF or it gets lagged by EMF?
Again.
Current lags by EMF, right?
Yes, sir.
EMF, you can say that current lags by voltage, or you can say voltage lags current. What about capacitor?
Leads.
Current leads. So voltage lags.
Yes, sir.
Right. This one also. Then we will use parallelogram law to add them up, to add all of them. Can I scroll it further?
Yes, sir.
Yes.
Next is phasor diagram. So this is the phasor for I naught. This is the phasor for voltage. It's V naught R. Is the voltage and current are in same phase. See what is V naught L? V naught L leads current by pi by 2. It's V naught L. It leads current by pi by 2, and it's V naught C. It lags current by pi by 2. So you have to add them up. Like you have to add V naught R, V naught L, and V naught C now. Now see, V naught L and V naught C are acting in opposite directions, so they get subtracted out. On subtracting these two, whether you will write V naught L minus V naught C or you will write V naught C minus V naught L, that basically depends which one is greater. V naught L is greater than V naught C or V naught C is greater than V naught L. That depends which one is greater. So I'm assuming case 1, like V naught L is greater than V naught C now. So when V naught L is greater than V naught C, then you will write this as V naught L minus V naught C now. And the angle between them is 90 degrees. So if two vectors are inclined at 90 degrees, then you write them as root over A square plus root over B square. So here one vector is V naught L minus V naught C, another vector is V naught. When you add them up, you will get net voltage. I'm representing that net voltage as E naught. So net voltage in LCR circuit, E naught is root over V naught L minus V naught C square plus V naught R square. See, V naught L, I can write this as I naught XL. V naught C, I can write as I naught XC square. V naught R is I naught R square. Now you can take common from here, like you can take I naught square as common from here, and you're left with XL minus XC square. Again, this is I naught square R square. You can take I naught common and take outside. So when you take I naught square outside, this will be I naught root over XL minus XC square plus R square. You can write this E naught by I naught as Z. E naught by I naught is root over XL minus XC square plus R square. This E naught by I naught is Z, so you can write your Z as root over its XL minus XC square plus R square. See, this Z is like equivalent resistance. In circuits having resistor only, we calculate equivalent resistance. For capacitor, we calculate equivalent capacitance. This is impedance. Impedance means combination of all reactance, inductive reactance, capacitive reactance, and resistor. So in resistor, we have R. In inductor, we have XL. In capacitor, we have XC. But we have when we have combination of all these three, then we have Z, impedance, SI unit is ohm. So you should remember it in this way. For resistor, we write resistance. For inductor, it's inductive reactance. For capacitor, it's capacitive reactance. But when you have a combination, then we calculate impedance. Impedance is like R equivalent or C equivalent. It's XL minus XC square plus R square. Once you have impedance, you can write the equation, the peak value of current. I naught is E naught by Z. Next, you can calculate phase difference between current and EMF. The phase difference is this is EMF and this is current. Can you see which one is leading? EMF is leading or current is leading? This is net EMF and this is current. Which one leads?
EMF.
EMF leads by some
EMF.
amount of phi. So from here you can calculate phi. See, this is a right angle triangle. Let's call this as O. I call this as A. I call this as B. In right angle triangle, I can calculate tan phi. It's AB by OA. It's perpendicular on base. In triangle OAB, we can calculate tan phi. It's OAB by OA. How much is AB? AB is V naught L minus V naught C. But OA is V naught R. V naught can be written as I naught XL, V naught C can be written as I naught XC, V naught R can be written as I naught R. So you can write your tan phi as I naught, it's XL minus XC by R, I naught R. Gets cancelled out. So that's the phase difference phi, XL minus XC divided by R. You should remember this relation as well as this relation for phase difference in terms of voltage also. So you can see that current EMF leads current by a phase difference of phi. So you can say that if equation of EMF is, current is I naught sine omega t, then equation of EMF is E naught sine omega t plus phi. So EMF leads current. Next we have power factor, we have average power, everything. So here power factor, cos phi, which we write as R by Z. See how we calculate R by Z. We make a triangle which we call impedance triangle. That's an impedance triangle. In this triangle, this angle is phi. We take this as XL minus XC. We call this as R. And hypotenuse, if I apply Pythagoras theorem, then this will be XL minus XC square plus R square. And this is impedance. So if I calculate cos phi from this triangle, cos phi is based upon hypotenuse. That's why I'm writing cos phi is R by Z. For average power, we have one standard relation. It's ERMS, IRMS, cos phi. So this is the combination of all circuits, LCR circuit. So in this circuit, the points that you should always remember is first is this thing, this expression of impedance, current, expression for phase difference, the two expressions for phase difference, equation of EMF and current, you should remember which leads, and power factor and average power. That's it. No need to draw sine curve here. You can't draw sine curve unless you know the value of phi. So you wrote up to this point. Note it down. See, numericals are easy. Like if you can do the previous numericals, like previous 3 topics, then it would be easy for you. Now, Abdullah, class is over. After this topic, class.
Sir, the equation of EMS is sine omega t plus pi by 2, right? Like E naught sine omega t plus pi by 2.
You know, no.
For EMF, sir.
Oh, sorry. Yes. Current is I not sine omega t. So if I'm taking current to be I naught sine omega t, then this is omega t plus pi plus phi.
Okay, sir. Thank you, sir.
Sir,
Yes.
sir, what is this OB?
OB is the EMF, net EMF. The total voltage. Like if you have 3 voltages here, like one V naught R, V naught L, V naught C, the sum of all is this OB, which is E naught, net EMF. So what I do here is I draw a parallelogram. This is V naught R. I take another side, then I complete the parallelogram. And this is the diagonal of parallelogram, which is representing the total voltage. So due to phase, it's behaving like a vector. So the net EMF is like resistance, resultant vector. Can I scroll it further?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, noted. Can I scroll it?
Yes, sir.
Yes, sir.
Yes, sir.
It's a bit up, like E0 by I0. Yeah, there. Fine. Okay, sir. Thanks.
Sir, can you zoom out a little bit?
Down.
No, sir, can you zoom out so I can see?
So what is that impedance?
Impedance is like the total resistance, you can say. Like for circuits having series combination of resistors, we like term like equivalent resistance. Just like equivalent resistance, this is the total obstruction offered by the circuit. That's what we call impedance.
Okay, sir. So can you scroll down?
So how did you get the value for phi?
Phi.
Yes, sir. From the triangle.
Say from the tan phi, like in this triangle, tan phi is perpendicular upon base, right? It's a right angle triangle.
Yes, sir.
This is right angle. So tan phi is perpendicular upon base. Perpendicular is parallel to this side, which is V0L minus V0C, and base is V0R. Okay, this AB is equal to V0L minus V0C.
And also that cos phi part.
Okay, this cos phi part. This I get from this equation, this triangle. I made a triangle, impedance triangle. This is known as impedance triangle. In impedance triangle, the base is equal to the resistance. The perpendicular is equal to XL minus XC. When you take the Pythagoras theorem, then this hypotenuse becomes equal to Z. So when I calculate cos phi from this triangle, that's based upon hypotenuse R by Z. This is perfect.
Okay, sir.
Thank you, sir.
Okay, so let's stop here. We'll
Thank you,
continue
sir.
this in the next week. Okay, love is bye.
Thank you, sir.
Bye.
Yes.
Thank you, sir.
Thank you,